All right. Well, I mean, I know we're supposed to be on fall break, but the exam will be this Thursday. So, I mean, if you don't want to show up, remember I have my policy that if you do better on the final than you do in the midterm, then, all right. So, exam is going to be a week from Thursday. So what we'll do is after fall break. So fall break starts Wednesday at what, 4 p.m. So you got to show up to all your classes until 4 p.m. on Wednesday. Yeah. I think classes that begin after 4 p.m. or 4 p.m. or after on Wednesday are considered canceled because of fall break. But anything earlier in the day on Wednesday is you are supposed to show up to. Okay, so do that. Show up to those classes. But in any case, so we won't be meeting on Thursday because of that. So on Tuesday next week when we come back, so a week from today, we'll review for the exam. So everything up through what we covered today will be on the exam. And then on Tuesday, we'll have a review. And then I might introduce some new material on Tuesday, depending on how many questions you guys have and that kind of stuff. But anything new we introduce on Tuesday will not be on the exam. All right, so the cutoff for the exam is end of class today for content on the exam. Okay, so just I'll give you the 30-second spiel. As usual, the way my exams work is if you bomb this one and you do better on the final, I'll replace your midterm with your grade in the final exam, not the other way around. So a 0 and an 80 turns into an 80 and an 80. All right, so you'll know kind of where you stand in terms of sucking at the material. So hopefully it's relatively low stress from the perspective of you get a do-over if you bomb it. Okay, but I don't go the other direction. You can't get 100 on the midterm and skip the final and then get 2 100s. It won't work that way. My exams, I mean, I usually will say, oh, you have an hour and 15 minutes to take it. The exam will be short answer, and essay type things, no multiple choice. I don't do multiple choice. I think they're stupid. Number of questions, I'll say however many questions it takes to take up an hour and 15 minutes, but very, very, very often that number of questions is 10. Mostly because that's evenly divisible, like 100, that's 10 points a question, that kind of thing. So expect 10 questions, but I reserve the right to make it 8 or 12 or something like that, but expect 10. What I'll do on Tuesday, because I haven't written the exam yet, what I'll do on Tuesday is I'll go through all the slides that we've done up to this point, and things that I deem that kind of pop into my head as being important, I'll point out, because those are likely things that I'll make questions based on. So you can focus your studying on those things. All right. And then any questions you have over any of the material we've covered up to this point, come with those on Tuesday, and I'll be happy to go over any, review any topics or anything like that. Otherwise, I'll just go through the slides, tell you what I think is important, what's not important, and then when nobody asks questions, we'll just keep moving on with material. Sound good? All right. So let's see, we're supposed to introduce, I think at the end of class last time I said I needed to introduce arrays in order to do our next thing, right? Okay. Because we had a issue. Let's see, do I still have it open?
Did we solve this problem with a $sign?
No, because of we have to introduce arrays. We had 2 different size registers. Here, let me just open it so we could point out the issue again, and then we'll talk about arrays. So I don't remember exactly what we were trying to pull off. Okay, so we were trying to do a, so here's our message. Hello, we were trying to do something where we,
$2 sign.
yeah, had the $sign. So this is that's the hex for $sign. Is that what that guy is? It's 86H.
It was the cross.
Oh, the cross. That's it. Oh, that was on you, right? That was extra credit, right? See, what's up? Yeah, he doesn't he deserve extra credit?
No.
It's not going to help him.
Do you want Skyline?
Huh?
You want Skyline?
Yeah. You're going.
I can.
Well, Nate, are you going to Cincinnati?
Yeah.
Yeah, I'll take Skyline and just tell me how much I owe you when you come back. Yeah, however many cans you want to get or can carry. Skyline Chili. That's the only reason to go to Cincinnati. And as evidence,
That's the most excited I've seen you ever.
Oh, hold on.
Like, seriously.
Do I still have it open? Oh, I must have changed this guy for it when I reloaded earlier because I had talked about Skyline in my class earlier today.
Is that why there's
Is
a
it-
picture in 250? All of them?
Oh, yeah. The entire video, well, I mean, it starts off as just, Skyline on the screen, and then I switched the camera to me eating it. Well, I was pretending to eat it because nobody brought me Skyline. And I made a mention of you in class. Yeah, so.
Their menu page.
What's up? Well, it is food.
It's just called cheese though. Look at the mounds of cheese.
Yeah.
Skyline is epic. So it's spaghetti with the kind of, let's call it the proprietary Skyline chili on top, which is it's very unique taste. And then, 6 pounds of cheese on top of that. Yeah, and it's legit.
Before
Totally.
I left, you could make it a Skyway for free, which is they doubled the amount of cheese.
Really?
Yeah.
They what?
Double the cheese?
Double the amount of cheese.
Yeah, because I actually have a Skyline chili by my condo in Florida where I go in the winter. It's walking distance from my.
That's why you have that condo.
Totally, it is.
That's why you have that condo.
So I could walk to it.
The one not in the 50-mile radius of
I
Cincinnati.
know, yeah. Totally epic. All right. And I'm sure it was started by some old person who retired from Cincinnati who went down there and well, they don't have one of these here. What am I supposed to eat? So something like that. But yeah, whatever you can carry, let me know and I'll give you money. Or I can give you money ahead of time to get it, whatever makes you happy. All right, yeah, so this was the cross. So we decided we were going to terminate our strings with crosses is the idea, which would then allow us to be able to, in theory, if we used our own function for our own procedure, rather, for printing out our new kind of string, our cross strings, right? Cross strings. Yeah, good enough. Then we could handle that situation. Well, so what we did is we moved into CX, the offset of our message. So this gives us the base address of our message relative to the data segment, right? Then we tried to move the value at CX. So that would be the H. This is what we were attempting to do. We were moving the value of CX into val. All right? And actually, I think that should have worked. I think we can move the value of CX into val. Was that word complained? Maybe that won't work. Val's
Yeah, that's working.
yeah, val's a DB. So yeah, that should be a data byte. That should be fine.
Well, shouldn't it be CL? Or the...
Well, but we moved into, the issue we had is we were using 16-bit registers here instead of 8-bit registers, and we either have to use all of one or all of the other. But we moved into CX, the offset of this message, which it really has to be that. That'll actually be kind of our next topic we're going to talk about. We're going to be talking about tonight, actually, in the class. But we're going to be talking about some of the mentality for different size register sets and things like that, probably beginning after the midterm. But when we move a memory address, we're moving in here a 16-bit address. So we have to do that because there's no guarantee that that address is going to require less space than that because we don't have control over it. Realistically speaking, we can make a pretty good guess that this value should be lower than what's required by a 16-bit number because this offset is relative to the base address of the data segment. And since the base address of the data segment gets generated when we start this thing, and it's kind of starts off in early memory, it's probably a relatively low memory address, which shouldn't take 16 bits to represent. But notice that I used the word probably several times in there. We can't count on it. So bottom line is that this guy right here returns a 16-bit memory address because it's a 16-bit architecture. Actually, 8086 is an 8-bit architecture, but offset gives us a 16-bit address. One of the things we'll talk about is why there's different size address spaces. So we're moving into that, the address. Then we're grabbing from CX the value at that, which should be a byte. Now, what Josh was saying is maybe we do, give me the value at CL, right? The value at CL would match the size here. Actually, yeah. This should not work. That should not work.
Because it's going to return a 16-bit value.
Yeah. So this does crash. This is where it crashes right now. Yeah. Okay, perfect. I thought he had said it does work fine.
No, you just said it crashed.
Oh, okay. Good. This should not work. The reason this won't work is the value at a certain bucket in CX is going to be a 16-bit value because CX is 16-bit, right? We're trying to shove it into something that's a data byte. Now, we should be able to do something like a DW, and now it should work there, but it will break later on. I think we'll get past this line here. Do we get past that line with a DW?
No.
It still crashes? What is here, let's just run it real quick. So we can take, that's a different issue. So we would need to do like move, are we using BX, CX? We can do it in AX just for the time being. So we'll move into AX, the value of at CX, and then move into val AX. Oh, I'm sorry. No, that should have worked. Val is a data word. 16 bits. Why didn't that work? Oh, it's still showing AX, CX. Oh, the same problem.
What?
I'm trying. It's not treating this as an immediate
Well,
value.
it's
It's not an immediate value.
It's an 8-bit value because it's H. So it's an 8-bit value.
So you're saying this should work?
CL.
Well, no. I mean, you're telling me that this boils down to an 8-bit value.
It should.
Okay, so then this should work. The value that comes out of this should be 8 bits. And I'm going to try to stick that into an 8-bit register. Yeah, see, that's not the reason why it's not working. The reason why this isn't working is our options for move are register, variable, those types of things over here. And then this can be an immediate value, but this is not an immediate value. This value is a... has to be, well, no, that should be an immediate value.
Yeah, it is. You get to move it.
So you're saying that should work.
Yeah. No, didn't.
What it's complaining about is these are the wrong parameters for move. So if we go over to our documentation, let's see.
Then would you have to store it?
Well, let's just look, we'll look at the assembly. Is this our, let's do 8086 instruction set. I have this linked on the website, but
Why does there have to be brackets on that move?
that gives us the value at that memory address. Because CX, I'll make this bigger here in a second. This is starting to relate to arrays anyways, this is fine. When I move into CX, the offset of message, I'm putting a memory address in here.
Why are you using CX?
No good reason. Just a general purpose register in this case.
Then use SI. SI will work.
So you're saying CX, because it's the counter, is getting blocked here?
I think it's because it's I don't know, but I know that SI does work. And you want to use AL.
Oh, okay. All right, well, let me finish explaining this other thing first. That's interesting. So that means they're protecting CX. All right, whatever. So this guy right here, offset of message, is going to give us a memory address. We're shoving that memory address inside of this index, inside of this register. This should be a general purpose register, but it seems like CX might have some protections on it. But so this guy holds an address. This says give me the value at that address. Make sense? So now we're back to the question, why does SI work but CX does not?
And you probably want to use AL instead of AX.
Yeah, it's fine. I'm more interested in the rationale behind.
Why that?
Yeah, let's do 8086 registers. Really, this should be the documentation for this. I guess we could just go right to the That'll actually be a more interesting thing for us that I don't think we've seen in here yet. 8086 user manual. So this is from, I don't know, 1980 or something like that. So imagine your computer today coming with, have we looked at this in here yet? We looked at it in the evening class, but we haven't looked at it in here. And I'm not going to go into any sort of detail with this. I just want to scroll down to our registers so we can see the original explanation of what the different registers are for. Okay. Yeah, so imagine if your computer came with a manual that's 208 pages long. That's how computers used to work. They would tell you how to talk to your computer. I mean, to use a computer in late 70s, early 80s, you write some assembly instructions.
Did they also come with schematics?
I think so, yeah. Actually, back then it was pretty common for your computer to be a kit computer, where you built it.
Until when? Until when were you not buying kit computers ever?
I mean, I'd be making no before that. I'm making this up. I'm just guesstimating, but I would say mid 80s is when it started becoming common for places, and really Apple was the dictated this. They were the ones that were saying, okay, it's no longer a hobby for electronics people. Now it's something that consumers might be able to use when they started introducing word processors and that kind of stuff. So somewhere in the mid 80s probably is when you could go into like a Radio Shack type place, and they would have a computer that was already put together. And it may even have been, there was probably a point in time there where places like a Radio Shack would take a kit, put it together for you, and then charge you a premium for that. Not necessarily dissimilar to, I'm sure Milwaukee PC probably does this. If you want to build a gaming machine or something like that, you could probably go into Milwaukee PC, tell them what you're looking for, and for the price of all the parts plus some labor percentage, they'll build you the machine, right? And you walk out with a completed computer rather than a bunch of boxes of motherboards and memory and stuff like that. So I'm sure there was a transition period there, but now you can go to Best Buy and you walk out with a computer that works. It's already put together is the idea. Okay, so this is the manual that would have come with this way back when. I kind of want to get down to our, so here's like schematics of how the bus interface and processor and all this stuff works. But I just want to get down to the registers so we can look at the official documentation. This is what a computer looks like. What's that? Oh, that's ribbon cable and the circuit emulator. All right. Yeah, this is what the actual processor looked like. So here's the pinouts. Today, when we think about processors, they're squares, typically, right, with a bunch of pins on the bottom of it. So here's an early processor where, it's elongated and all the pinouts are out here to the side. We didn't have the technology to have the to manufacture a processor that had sturdy pins coming out of the bottom. All right. And I think you could still order 8086 processors like on Amazon and stuff for your little like electronic kit type stuff. You could build stuff with an 8086 processor with like Arduinos, that kind of like kit things. Okay. Yeah, so we have here's our process. They break these into two different groups. We have our data group, and then we have our pointer and index group. So it looks like they're protecting, at least the emulator is. I can't say for sure that it's not the emulator doing this as opposed to something else. But SI is specifically for a source index, so it's kind of built for what we're doing here. Here's a memory address of this position. And then we have a destination index as DI, base pointer, stack pointer. So these guys are all built for holding memory addresses, although they are general purpose registers. It's just interesting that the way I would argue is that these guys lend themselves to certain things. AX lends itself to accumulating things, adding and things like that. CX lends itself to counting because so many functions that are built into the 8086 instruction set rely on certain things being in CX, and it uses that for counting stuff. But physically, these guys are not, they're not different from each other. They're all 16-bit registers. So this is kind of interesting that there is some level of security, and I don't know if it's at the architecture level or if it's at the emulator that's enforcing some rules. So I don't know the answer, but it'll still be on the midterm. So yeah, just very interesting. So in any case, SI is a general purpose register, but it's lends itself to pointer stuff. And so we're putting a pointer in there here. So we're going to move into SI, the offset of message. And then we're going to move into, in this case, AX, the value at SI. But we know the value here should be 8 bits. So you're saying if I move into AL, SI, that should work. Okay? Because you know that the value at that memory address is an 8-bit value. That's our idea here, right? All right.
It's going to error out the next line.
Okay. So then what we're doing is we're moving into, what was val? Val is our, actually this could be a double byte now, or a data byte now, because we know that AX, so this is going to be AL now, right? So we're moving into AL, the value at that memory address. We're moving into val. So actually, just out of curiosity, could we have moved it directly? Did it treat this as a memory address or as an immediate value? Okay. All right, so we'll move this value, which is not an immediate. No, it should. Well, that's weird. So it must be that you can't move. As long as this is a register, you can move a resolved value. Let's look at move real quick, just so we can clarify that for us. Because when you look at the commands in here, it gives you what are the legal inputs, the legal parameters for this guy. So we go down to move, it'll be register to register, register to memory address to register. There'll be immediate values, so we're interested in what the ones dealing with immediate values say. All right, so where's an immediate? So immediate, yeah, immediate can go into memory, immediate can go into register.
What's the SREG?
Don't know if I know the answer to that.
But it means that still can go into memory. Whatever
Yeah.
it is.
Oh, I bet you this thing is why SI works, because it's specifically for string operations.
Well, so CX is too.
Well, CX is for counters, for loops. So this is what it lends itself to, where this guy.
String options and then loop operations. Then loop.
Yeah. But this is going to be string operations related to counting. This is going to be string operations related to the address. So I'm guessing that it must enforce those at some level. Well, I really wouldn't think they do that at the architecture side. It has to be at the. Yeah, at some point we'll probably stumble upon something that we'll clarify that. Let's not spend any time on it now, but that immediate value should be able to go into memory.
But is it an immediate value?
Well, it must be from the perspective that we can put it into a register.
Or is that a register that it stores?
Oh, I'm sorry, this guy. Here's an immediate into a register.
But is it not a register into a register? Is that how it thinks about it, or not?
Doesn't matter, because we can say register into memory works too. So that guy, the address at SI, or the value at SI, is either going to be an immediate or it's going to be a register. But it doesn't seem to be treated as either of those here, because we weren't able to load into val. the value at SI. Let me try. Let me make this a DW. Yeah, doesn't really give us anything beyond just.
If you move SI straight to DL.
Oh,
you could move it straight.
That's actually an interesting point, because now that goes back to what you're allowed to put into AX. So if we go back here and we look at what DX is for, word multiply, word divide, indirect IO. So it seems like that would fall into IO stuff. This would be a data register. So now we can move into DL, the value of, I'm sorry, move into DL, the value at SI, and it lets us get past that. Yeah, the error is someplace else. Okay, so it lets us get past that. So this guy is not being protected. I can move into DL the value at this memory address, which we know is an 8-bit value. At that point, we no longer need val, right? This guy is no longer a necessity. Okay, so we'll move into DL, our character. We'll move into AH, the 2H, which is our print char. Is that print char with echo?
What do you mean print char with echo?
Display char with echo. Display char with echo. DOS 8086 API.
Well, no, the echo is the when you write it in. It's not printing.
Is this it? Yeah, what's 2? Write character to standard out.
Yeah.
Oh, the read in was the echo one. Yeah. I get what you're making fun of. Okay, I got you. Yeah, writing doesn't make sense because you are echoing.
Yeah.
So write with echo would be 2 writes. I wouldn't put it past Microsoft.
Verbose mode.
just in case your video card buffer missed it the first time. I mean, honestly, how often do you get extra artifacts on your screen in Windows? Well, historically, Windows, you often. Yeah, Windows now is pretty good, doesn't it?
No, I don't think it is very good now, but they've gotten rid of the artifact.
You don't think Windows is pretty good now?
I think it's cancerware. It's so bad.
In what way?
Forced updating, everything they're pushing onto us, and the search bar. I could talk to you for 2 days about how terrible the Windows 10 search bar is. I can install an application.
So you're going to switch to Mac?
God no.
Correct response there would be immediately begin vomiting.
Sorry.
You got to ward a guy before you say something like that. Even got Joel laughing there. That's one of my goals for the day. All right. So we'll move into SI, the offset of the message. We'll move into DL. This is the data, the character that we want to print will be in DL, that we want to write, I'm sorry. Then we'll move into AH2H, which is the write character to standard out 8086 instruction. Then we'll interrupt the CPU calling DOS. And so this should give us just the H for this particular dealie. It's yelling down there. So let's jump down there real quick and just fix that because why is it getting to that? There. Oh, I hate it. So let's just cut this for a second, and then we'll. All right, so we want to just get the H out of this guy, so let's move this and just hit run, and there's our H to the screen. Okay, so now we were writing the Superprint, and Superprint should be able to go through I think our intention was Superprint should be able to go through a string that is terminated with a cross, right? and give you everything up to that point, because we're kind of saying that it's more likely that you're going to have a dollar sign in your string than a cross. Why is it more likely you're going to have a dollar sign in your string than a cross?
Money, currency.
Well, and your keyboard is missing the cross key. Right?
Valid point.
Anybody's keyboard have the cross key on it? We should start selling Christian keyboards. the integrated cross key. Yeah, that's a point. All day long, that's a point.
Just make a little button and then the cross, like people did for the hashtag. Because getting to the hashtag symbol or like the number sign isn't.
Oh, is it convenient?
Yeah.
Okay, but getting to the cross is impossible.
Yeah.
It's like the alt code you have to type in.
Yeah. Okay. So let's go ahead and put this guy back in. All right, so Superprint is a procedure. Here's our begin. So we're going to compare. Okay, so we're actually loading into, let's see, this guy is going to compare what is currently in SI. Okay, no, we need to rewrite some of this. So this assumes the base address is in DX, and that's not the case anymore. All right, so we need to compare. We're looking for the current value, which is in DL. We're comparing that to an 86H. But actually, for Superprint, the base address is in, let's do SI here. That'll work for us. So we're going to compare. Will this work? Can we say SI 86H? So this will compare whatever is currently at the value at memory address SI to the cross. If that's a 0, which means that they were equal, then we're going to jump to SPN, which just returns. Otherwise, we'll move into, okay, this is where we're done here. Otherwise, we want to move into DL, the value, what happened?
What's JZ?
JZ is jump if 0, which is the result of a compare.
Yep.
So here, let me just show that real
So
quick.
would that be similar to jump not equal?
JNE would be jump if not equal.
Yeah. So wouldn't that be the same thing?
I don't think that, is there a JE?
Yeah, JE's what I use. JE's jump.
Jump if equal. Okay. Well, here, let's just look at the jumps real quick before we go. J comes early in the alphabet, right? I only think in hex, so it's a. All right. Yeah. Here's a bunch of jumps. So let's just flip through these guys real quick. Actually, here, let me start with compare, and then we'll come back to the jumps, just so we can see them. All right. So this is CMP. The result of a compare. CMP is for comparing two things. This is kind of our assembly language version of an if statement. All right, so we're asking a question. The result isn't directly stored anywhere. It sets a series of flags that we can then check to see what the result was. Okay, so it's not stored anywhere. Flags are set according to the result. So the syntax for this is, compare, then two parameters. Let's see, so here's an example. If we move into AL5, move into BL5, so two immediate values, then we compare AL and BL, which are equal. The AL will still be equal to 5, and the 0 flag will be 1. All right, so our 0 flag will be on. It's not 1, it's on. So now we can jump if 0. That's jump if the 0 flag is set. So that is a jump if equal, right? Okay, but so if we scroll down now to the jumps, we have a whole bunch of different jumps. Okay, so this guy is a jump if first operand is above the second operand. So this is following a compare instruction. So we would do a compare, two values. If the first value is larger than the second one, a JA would jump to this label if that was true. Make sense? That's a jump if first guy is above or equal, below or equal. Carry flag is set. So let's see, this guy is not used directly for compares. This can be any time where there's a carry. So if you do some mathy stuff, you can do a jump if there was a carry, if you need to handle an overflow bit or something like that. So this is unrelated to, not necessarily an exception. Let's say you have, if we talk about this in terms of Java, if you have an int A is equal to 2.1 billion, you know, almost the maximum value of an int, and then you add to that a million, you know, something that will take it over the maximum size that an int can hold, which is 32 bits. So now we're at 33 bits. In assembly, if that math had happened, we would have the carry flag set because we've lost precision. Depending on which math instruction you use, sometimes that overflow then gets stored someplace else. So you can still deal with that. So in this particular case, you might want to jump if there was a carry so that you can deal with that extra, the extra value. Make sense? So sometimes you might do some logic where whether a carry just occurred or not might be helpful. Okay? But that isn't directly related to the compare instruction. The other ones were. Same thing here. So this is jump if the CX register is 0. So you imagine have we done the loop instruction yet in here?
Yes.
Just a simple example of loop that use CX going down to 0. Okay, so loop is probably implemented in terms of this. You keep jumping, you keep going back to a beginning label until CX is finally 0, and then you jump here, past the end of it. Okay? So jumps are how we get around inside of our program based on different things. So here is the JE. So jump if equals, this is, if I'm taking this back to our Java days, I would say this is syntactic sugar for jump if 0. It's the same thing. So this guy is if the 0 flag is set, then jump. Where technically if two numbers are, because the way compare works is it does subtraction. So if I have 5 minus 5, that's 0, so the 0 flag would get set. Make sense? So those two are equal because the 0 flag is set. You take any two numbers that are the same numbers and you subtract the first one from the other one, you'll get a 0, which will set the 0 flag. So JZ is functionally equivalent to JE. But JE is easier to remember because now you don't have to worry about what the state of the flags are following at the compare. You know, we were relying, when using JZ, we're relying on our knowledge that the 0 flag will be set in the event that the two numbers were equal. Where just using JE, we're saying, oh, jump if they're equal, following a compare. Make sense? All right, so this is set by the compare instruction because we can't set the flags directly. So, question then, following up on that, why does JZ exist? Why wouldn't we just always use JE? Are these guys, does JZ and JE, aren't they functionally identical?
Is it just what you said? It's just syntactic sugar. It's just a little bit extra they threw in there because they knew JZ would be used often enough that it warranted.
Or that JE would be used often enough? Is that what you meant or not?
No, I meant like JE is the one that you would use over JZ, right? Like for if you only had one, you would need JE. JE does what JZ does, right?
Well, yeah, these guys are identical to each other. They literally both do the same thing. We could use them interchangeably. But now from a programmer's perspective, JE logically makes sense when we want to do, jump if two things were equal to each other, regardless of what the state of the flags are under the hood, right? You want to jump if two things are equal, you do a JE. Even though we all now know that JZ will do the identical thing. Okay, but calling JE doesn't require us to understand what the current flags are set to. Now, having said that, would you ever use JZ? Yeah, I mean, there might be situations where you're not necessarily comparing two values, but you're interested in whether the zero flag is set, right? So jump if zero. So they do both have a purpose. JZ could always be used for both. And hold on. JE could also always be used for both since they literally are identical. But JZ makes some sense if you're just checking the zero flag. JE is a hack if you're just checking the zero flag, right? Because you're saying jump if equal when you never even did a compare. You're actually just having it check the zero flag. Makes sense? But because you know how the guy works under the hood, it happens to check the zero flag. All right? So it doesn't matter which of the two we use here, but I think I agree with you. We should use JE because that makes more sense to a human, right? And this stuff already makes less sense to humans than it maybe should. It's kind of the idea, right? All right, so we'll do a compare on the value at SI with the cross. If those guys are equal to each other, we're done. That's our termination, so we'll go ahead and return. Okay. Otherwise, we'll move into DL, the character we want to print. We'll move into AL, or AH, sorry. What we want to do, and then we'll interrupt 21H. All right, and then there's our SP end. Yeah, we'll just leave it. Actually, do you know when we write a string, does it also put a carriage return in, or does it keep it on the end of the line? End of line? Okay, so we don't need to do a carriage return fake thing. All right, so before I go farther here, let's just look at the rest of the jumps. So there's jump if equal, jump if the first operand is greater than the second operand. This is signed, so was jump A, JA, unsigned? Yeah, JA is an unsigned. So it completely ignores negative numbers. So those guys are not necessarily identical, just very similar. Why do you suspect that there's a jump for one number being greater than another in both an unsigned and a signed form? Why is there a difference? Or is are they just trying to give more instructions to look impressive? Go ahead. Well, the short answer is yeah. That could happen. Why? Why would different flags be set? Okay, so what is that? When you have two numbers, if we're doing math with unsigned numbers, isn't that easier math than doing math with signed numbers? Substantially so, right? That gets back to our discussion about two's complement and that stuff, right? So if you're doing subtraction, for example, with signed numbers, now we got to start encoding numbers and then doing addition. We encode them in two's complement form, right? And then we do addition. Whereas if we're dealing with unsigned numbers, we don't have to worry about it. There's no extra work. So unsigned math is faster. So wouldn't it make sense to use the commands that are specifically geared towards unsigned stuff if we know for a fact we're dealing with unsigned stuff? If we're trying to be efficient and put yourselves in the shoes of a programmer from 1980, efficiency was probably significantly higher on your priority list than it is for us today, right? Because we would notice speed. An 8086 processor really isn't going to do a great job of keeping up with like a pencil sharpener today. It's actually probably not a completely true statement, but you get the point. Yes, it's not going to do real well against your Intel Core i7 quad-core processor, with 4 megabytes of L2 cache or something. It's not going to keep up. This is Usain Bolt versus me again. Only worse. Probably a lot worse, actually. That'd be a good trivia question. Which is the larger difference in speed? An 8086 processor versus a modern Core i7, or Usain Bolt versus Lippmann? Show your work. What's that from Big Bang Theory? What was the quote? You know, like, well, is that a metaphorical question, or would you like to actually do the math? And the mom goes, I'd like to do the math. Remember that episode?
I don't watch.
You don't watch the show?
I don't watch a show with a laugh track. That's weak.
Do they have a laugh track?
That's like, if you watch it without the laugh track, it's like depressing. They're like, do it on YouTube. You should watch it. It's just like, it's really depressing to watch.
Really? So you're saying well, I think the show's funny anyways. But you're saying without the laugh track, there's a psychological thing that changes.
I think a little bit, but I also think that it's not very funny, personally.
I gotcha. So you just have a bad sense of humor.
I think I have an excellent sense of humor.
Well, clearly not.
Any TV show that uses a laugh track is weak, in my opinion.
I gotcha, because
You can't
they're
name
not
something.
standing behind their product.
Yeah, I should be laughing. You shouldn't be having other people laugh.
But why would you be laughing if you have a bad sense of humor?
Maybe I'll exhale through my nose slightly louder than usual.
Where's our jump of 0? Hold on. All right. All right, so yeah, the JB stuff that was jump if below, that's for unsigned, so we're down to signed stuff. So JG, jump if greater, is for an unsigned, or I'm sorry, a signed result of a comparison, which is more expensive. All right, let's see. And actually, I think there's different compares. There's a signed comparison there. We'll have to confirm that. No, they're not using a different one here. I'm not positive on that one too, so I don't want to advertise it. Jump if greater than or equal to, sign. Jump if less than, sign. Less than or equal to, signed. Shut up! Notice how that was significantly lower than I usually do it. That was more of a calm shut up instead of throw a desk shut up. Unconditional jump. So now this isn't on the result of a comparison. This just says go somewhere else. You know, we have labels in the code. So a label is, you know, just a word with a colon after it. So JMP just jumps there. We're not checking the results of flags or anything. We're just going someplace else. All right. Jump if not above is unsigned. Not above or equal to. Not below or equal to. No carry flag is set. Not equal to, JNE. Not greater, that's for signed. Not greater or equal to, signed. Not less than, signed. Not less than or equal to, signed. No overflow set. What's this one? No parity, that's a different flag, parity flag. That's the number of zeros compared to the number of ones. Jump if not signed for the result of these values. So like I mentioned, comparison does a subtraction. So if the result is not a signed number, then this jump would work. I don't necessarily have a great example to give you for that, but it's a thing you can check. Jump if not 0. Jump if there's an overflow. Jump if parity is set. Jump if the parity is even. So same even number of zeros, or I'm sorry, even number of ones. Parity is odd. Jump if signed. Jump if 0. So there's our JZ. Okay. So a lot of jumps, right? Okay. Why do you think we need so many jumps in 8086? Well, yeah. I think both of those have some accuracy to them. I don't think we're quite to where we need to be yet, but we're halfway there at least. So this is the second half of an if statement, right? Comparison is the Boolean expression, and then the jump is the what do we do with this Boolean expression. Does it ultimately evaluate to true or false based on what we're looking for? All right, so it completes that. Okay, now what bad answer did you give?
I said so it can be most efficient when using a jump. Like if you're doing a lot of jumps in a program, you're going to want to using the most efficient one.
Okay, especially historically, if we put ourselves in a programmer from the early 80s, efficiency is important. So we have lots of granular control over how we're going to jump in the event that we want to control our efficiency. I think that's a fair statement. Anything else you can come up with as to why we have so many jumps? It's probably related to the granular control thing. Go ahead.
Because it's an 8-bit architecture and you need something to fill out all those instruction sets.
Okay, so basically because we have room in the instruction set for more instructions, we might as well use it. Well,
Because like there's some
really
instructions on there that
not,
say, like,
it's not necessarily a horrible premise. Yeah, I mean, and really that gets down to something we talked about earlier in the semester about reduced instruction set processors versus expanded instruction set. Intel architecture is just the presumed expanded instruction set. So reduced instruction set, try to reduce the number of unique instructions we have. His argument is, hey, we have room, why not use it? We already have the memory. It's not costing us any more to put this onto the chip. We have space, so why shouldn't we use it? I mean, that's not really a horrible answer. I mean, it's
No, yeah, that's what I was
Yeah.
thinking. Was like,
it's more right than I thought his original answer was, but I'm starting to appreciate his answer a little bit more, I guess.
because there's some instructions on there that just seem completely useless.
Okay. Yeah, and there's probably truth there. It comes down to that syntactic sugar thing, where, hey, we have the room for it. Why shouldn't we give a convenience instruction that allows the user to have to remember less detail because there's a lot of detail going on in here? Okay. Any other reasons? Still haven't necessarily hit on the one I'm thinking of here. I mentioned it a few minutes ago. I don't think Josh and Alex probably weren't paying attention because they were babbling about something. Was it class related or like gaming?
Computer.
So not class related. I got it.
Who's gonna bring it now?
What's up?
I was building a PC and I was like, hey, should I put an 8086 card in here? And he was like, no, that's stupid.
So you're shopping for computer parts for a computer you're building. I get it. Yeah,
Slightly, for a minute.
you don't have to get all defensive about it. Yeah, I get it. During my class.
I'm waiting to hear this answer to this question.
Okay, so it's on you now. What's the answer?
I already gave you my answer.
No, I need a better answer than that
Warming
crap.
up to it. I'm gonna let it. You can
Let it simmer?
sit for, yeah.
All right, anybody have another rationale for why we have so many jumps? All these
Be able
jumps.
to get around the code without having to repeat the lines that you've already repeated.
Okay, I mean, certainly kind of the purpose for jumping at all is to be able to get around to different portions of code. We're jumping from label to label to label. So, I mean, there's truth to that. That's why the idea of a jump even exists, right? Now, all of these jumps have something in common. What's common to every single one of the jumps? Well, except just the normal jump, just JMP. All the other ones, the jump if not equal, all that stuff. What's common to all of those? What do they have in common to each other? Go ahead.
They take a label.
Okay, that's
Was it?
a true statement. They all jump somewhere. Okay, so
They look at the flags.
they look at the flags. Every single one of them looks at the flags. Why is that an important statement?
Because we don't necessarily know how to look at the flags without jumps.
That's how we look at the flags. Jumps are our mechanism for looking at the flags. That make sense? We can't look at them. We can't manipulate them directly. They're manipulated as a result of other instructions. And we can't read them directly. I mean, with the emulator, we can look at it and say, oh, there's the flag, right? That's, we can do it that way. But realistically speaking, we can't see the flags unless we use some instruction that gives us access to it. Jumps are one of those instructions that allows us to do something based on the value of a flag. Make sense? So we really need a lot of flags. I'm sorry, really need a lot of jumps in order to work with all of the flags. So we have a set of flags that work I'm gonna keep getting confused now. We have a set of jump instructions that work with specific flags that we're interested in. And then we have a set of jump instructions that we can, say maybe are syntactic sugar that allows us to consider the result of a compare in a more human-like way, even though under the hood, it's still comparing flags. Make sense?
So then, for most jumps, do they only look at one flag? So then you have to put multiple jumps in a row to look at multiple flags?
I'm trying to think if there's flags that will look at jumps that look at multiple flags. I think there might be a couple, but
But for the most part, you'd have to use
if
jumps
you're
in a row.
only interested in in the value of some flags. I mean, at this point, we're trying to come up with a pretty contrived example of, I really want to know if the carry flag was set and the 0 flag was set and the parity flag was set. I mean, you got to come up with some sort of weird example where all three of those things become important to you, right? Then you would have to jump if one of them, jump again, then jump again. And if you end up in that, final secret room, that's when you do the magic that's like, okay, the moon's aligned and all three of those flags were set, so I'm going to go and do this. The other thing, you probably come up with some sort of math that forces those flags to be set for you to test it mathematically or something. Okay. All right, so for Superprint, we're going to begin. We'll compare the value in SI to 86H. If they're equal, that means that we're at the end of the string, so we'll jump to the end. Otherwise, we'll keep cooking here. We'll move into DL, the value we want to print. We'll move into AH, that we want to print. Then we'll interrupt, let DOS take over. What do we do after we print that value? Two things we want to do. Okay, I need to increment my index, right? So inc SI. So we'll add 1 to our base pointer to get us to the next memory address.
And then you need to jump back to begin.
Okay, which jump do I use?
You could just use jump, but you'd want to compare SI to,
Well, in this case, if
The fact that it's there, it's already.
yeah, I mean, this doesn't really take into consideration a poorly formed string. Our strings are all terminated by crosses.
yeah, but are we checking that here?
We checked it right here.
We checked it above it.
Okay.
If it's a cross, we're done.
Okay.
Otherwise, print out the current value,
Yep.
increment SI, and then jump to SP begin. Like that, right? Okay, now we're doing all this with jumps. Could we have also done this with a loop? Okay, how would we have had to do it with a loop? We would have had to figure out how many times we needed to repeat, right? And how would we have calculated that?
You just have to go through and count the characters until the cross, and then you'd store that into CX, and then just loop through that.
Then loop through again. Okay, so is one of these better or worse than the other? I mean, that seems like a lot of work that we're doing anyways.
You do what you were gonna do before you do it.
But we could maybe make the argument, again, if we never saw a dollar sign. Okay, I don't want to give away too much. Can you make an argument that we might want to do a loop for printing this out rather than a series of jumps like we're doing here? Why would it be worth the effort to go through and count how many characters we want to print and then print, rather than just go through and print as long as we don't see a cross? What's the advantage of that? Or can you give me a circumstance when that would be useful? give you a hint. Okay. The hint is efficiency. And it involves this guy right here. Every single time we see an int 21h, what does that mean to us?
Input output to it. Time.
It's expensive, right? This goes back to the operating system argument of a context switch, right? That's expensive. Every single time we do an int 21h, it's expensive. Now, if I have a string that's 10 characters long, how many times am I doing int 21h here? 10 times. So 10 expensive things. So can you give me a reason why it might be beneficial to go through and count how many characters that I have, how many characters I have before I actually display it?
Well, so what you could do is you could build another string.
That is the string without the
build it,
cross,
yeah.
basically.
Yeah. And then print that string
all in one go.
all in one.
If we detect that our cross-terminated string does not have a $sign in it, we could convert our cross-terminated string to a $sign terminated string and then call the single DOS API command to write a string. That makes sense? Saving ourselves time. Right? Does that make sense? But that's only if we didn't bump into a $sign. So one of the advantages that we're trying to build here with our superstring, or our superprint rather, is that we have cross-terminated strings for two purposes. One is Christian worldview, points, like mucho points, right? Is that mucho? Is that it's German, right? Chinese? It probably is. There's probably, I bet you it means something weird in Chinese. I'll have to ask Blade. What's up? Oh, hey, does mucho mean anything in Chinese? You never heard that word? Yeah, I know a couple of words in Chinese. Was it red dragon? I know how to say that in Chinese, and it sounds like something that's not that great to say in English. Well, yeah, right? Red dragon? Yeah, how do you say that in Chinese?
That's funny.
Blade taught me that.
Yeah, long with I think it's dragon.
Actually, Blade taught me that the first time I met Blade's mom. So I said that to her, and she just started laughing because she knows enough English to be dangerous. So, everybody you all know who Blade is, right?
No, these kids are too young.
Really?
Yeah.
He's been at like our get-togethers. He just graduated from our MSIT program.
He hasn't been there in a while.
He was just there the last time.
Maybe 6 months ago.
Really?
He wasn't there last Thursday.
Huh. Well, there's Blade with Mr. Gonzalez. Yeah, he's been to a bunch of our hackathons and stuff. But yeah, all my Chinese I know is from him. Okay, what was I talking about when that happened? Oh, mucho, right? What was I? How did I get to mucho? Oh,
You're talking
yeah.
about time.
Time, yeah. So that context switching is expensive. So if we can go through and, counting is fast, right? Computers are really good at mathy stuff. So if we can zip through real quick and come up with how many characters, did we run into any $signs? If not, if the count of $signs is 0, then we know exactly where the end of the string is, because we can keep track of that when we hit the cross. We have the index of the cross that tells us when we stop and say, oh, well, my count of $signs is nothing, therefore replace cross with $sign and then call the DOS write string function. One interrupt. Make sense? All right, so let's see, SP begin. All right, so we'll compare this guy. Are we at the end of the string? If yes, jump to the end. Otherwise, here's the character we want to print. Here's the print. Increment SI to move to the next character in our string. jump back to begin, do this again, over and over and over again, until we finally hit a cross. Then we'll jump if equal to the end, which tells us to return, which puts us back up here. So up here, we should be able to move into SI, the offset of our message, and then call Superprint on that guy. There's our hello world. And actually, that really proved the point. Did you see how we saw that come out? Let's reload that. It was very exciting. That was slow, right? Context switching. We just saw it in real time. All that I/O is really expensive. But there's our cross-terminated strings.
Is it possible to speed up the emulation so it just goes?
Let's see. Well, it's already, well, that's a step delay. I don't think that's going to do anything for us. I don't think there is a way with this. I think it'll be slow regardless. Even if we were just to run this through a normal assembler and run it. Because, we are literally interrupting the CPU 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times in a very short period of time, making whoever's on the CPU, the guy that, so that's us, I guess. Okay, so we are currently sitting on the CPU, and we're doing this instruction, which is fast, this instruction, which is fast, this instruction, and then this instruction. All of those are fast until we hit the int 21H, which then says, okay, we need you, our program, to pack all your bags, remember all the current register settings and all that stuff, and get lost, get off the CPU. Then the next program that was in line, whoever that was, maybe it was my instant messenger or something like that, he unloads all of his bags as he gets back onto the CPU, as he context switches onto the CPU. That takes time. Then we do our I/O, printing one character to the screen. Then our program goes and gets back at the end of the line, waiting for the CPU again. And then when he's finally his turn again, he then has to unpack his bags into the CPU, does those 4 little commands again, and then leaves the CPU again. There's a lot of waiting going on there. This is a pretty inefficient setup we have here. So it would be in our best interest to to just use the $ terminated string, or for the DOS API to not rely on $ terminated strings, rely on a character that doesn't actually exist in the language. Or doesn't exist on the keyboard at the very least. Make sense? All right, no homework over break. I will see everybody on Tuesday. Come with questions for the exam, and then we will. I'll deal with those, and then I guess we're going to talk about arrays. All right, I will see everybody then.